Hello there, this is a geometry video. It is chapter 6, section 1, just getting started here with polygons. And so today we're going to be talking about angles of polygons. So we have all kinds of different polygons up here on the board for you to look at. And before I get started, I want to kind of explain what's going on here on the board. I'm trying to define for you, if you will, the word diagonal. I know that when you have a rectangle, it's very easy for you to think of what a diagonal is. It goes from one corner to the other. But we actually do have a definition for a diagonal. And diagonal is a segment that connects any two non-consecutive vertices. So diagonal is any segment that connects two non-consecutive vertices. So just to be clear, in all of these polygons, you have vertices, which are basically plural for vertex. So all of these points here are where the two sides connect is a vertex. So this triangle has 3 vertices. This one has 4 vertices because it's a quadrilateral, 5 vertices for a pentagon, and 6 vertices for a hexagon. So a diagonal is defined as a segment that basically joins 2 vertices together, but it can't be consecutive vertices. And so consecutive means like right next to, right after. Like when you say consecutive numbers, it's like 2, 3, 4, 5, 6. It's one after the other. So if I were to start here, for example, and try to make a diagonal that would connect this point to the next vertex that's not consecutive, this would be the next consecutive vertex. So I can't connect it there. And then if I try to connect it over here, that's consecutive on the other side. So I can't connect it here. So basically a triangle has no diagonals. In a quadrilateral case, if I go to this vertex, again, I can't connect it to that one because it's consecutive. I can't connect it here because it's consecutive. So the only vertex left is to connect it there. And that would be a diagonal to a non-consecutive vertice. So there's your quadrilateral, has 1 diagonal. A pentagon then has 2 diagonals, as you can see here. Can't connect it there. Can't connect it there. So there are 5 total vertices, but 2 of them are no-go because you can't go right or left to that first consecutive vertex. So if you had 5 to begin with and you take away 2 of them, now you're only left with 3 options to go to. So you can go to that guy or to that guy for the pentagon. So only 3 vertices are in play. Uno, dos, tres. Okay, over here for the hexagon, same idea. You can't go to the very first one because it's consecutive. Can't go to this one because it's consecutive. But then that leaves you with, let's see, if you don't count this one, it leaves you with 3. So you have 1, 2, 3 there. So that's kind of how that works. Just wanted to be clear on what a diagonal is. But what you can see from these diagonals when you actually draw them out, and you can keep drawing more figures if you want to, is that each figure has triangles within it once you draw the diagonal. So a triangle has only 1 triangle in it, no diagonals. When you draw the diagonal in a quadrilateral, you end up with 2 triangles. And in a pentagon case, you end up with 3 triangles. In a hexagon case, you end up with 4 triangles. And what you're supposed to be seeing, there's a pattern that the number of triangles that are in the figure is basically dependent on the sides minus 2. And it's minus 2 in a way you can think about that because you subtract for each vertex, you subtract 2 consecutive vertices. Every vertex has 2 consecutive vertices next to it. So you always take the number of sides and subtract 2. And we also know now that when you do that, each triangle has to have 180 degrees. So when you combine these 2 triangles together, you get 360 degrees for a quadrilateral. Here, if you take 3 triangles and times them by 180, because each triangle would be 180 degrees, you would get the amount of degrees in this figure, and so on and so forth. So what I have for you right here is a theorem, polygon interior angle sum, which basically tells us that the sum of the interior angle measures of an n-sided convex, oops, and I forgot a word there, convex polygon. Let's add that there. Let's not use the highlighter to do that. I'm glad there's some space right there for that little word. Is, so the interior, the sum of the interior angle measures of an n-sided convex polygon is n minus 2 times 180. So the number of sides minus the 2 vertices that are consecutive times 180. And we're going to use that to do some examples here. It says find the sum of the measures of the interior angles of a convex heptagon. Well, a heptagon, if you didn't already know, is a polygon that has 7 sides. So I have to know that, of course, first and foremost. If you don't know that, you're going to have a hard time. So n is the number of sides, so it's going to be 7. So the sum of the measures of the interior angles of a convex heptagon is going to be n minus 2, so 7 minus 2, times 180. 7 minus 2 is 5, and 5 times 180, 5 times 180 is going to be 900. So when I add up all of the measures of the interior angles of a heptagon, I'm going to get 900 degrees. So now it says in part B, find the measure of each interior angle of quadrilateral ABCD. So here we have basically, I want to find the measure of each angle. Before I can do that, I need to solve for x. So because this is a quadrilateral, it means that the number of sides is 4. So I first and foremost have to know how many degrees are in the entire figure altogether. So that I'm going to go 4 minus 2 times 180, which is going to give me 2 times 180, which is 360. So I know that all of the angles inside of A, B, C, D are going to add up to 360. So now I can do a little algebra and say 90 times 2, because there's two 90-degree angles, plus 3x plus x, so I'm going to get the 3x from angle A and the x from angle D. All of that should equal 360. So if I subtract 180, which is what 90 times 2 is, and I combine my like terms, 4x equals, excuse me, 180. When I divide by 4, 180 divided by 4 is going to be 45. So x equals 45. But they don't want me to just find x. They actually want me to find the value of the angles. So we know that angle B is 90. It's marked a 90-degree angle. We know that angle C is 90. But angle A is equal to 3 times 45, because it's 3x. And 3 times 45 is 135 for angle A. And the measurement of angle D is x, and x was 45. So that is how we get our measures for that little guy. So now we're going to let you try this one on your own, and then we're going to move on. I mentioned earlier that you kind of want to know all the different names of the polygons. So we have right here the name of the polygon depending on the sides. Obviously 3 sides triangle, 4 sides quadrilateral, 5 sides pentagon, 6 sides hexagon, 7 sides heptagon, 8 sides octagon, 9 sides a nonagon, 10 sides decagon, 11 sides hendecagon, 12 sides dodecagon, and then once you get past 12, we just call it an n-gon. So if it has 13 sides, you just call it a 13-gon, a 15-gon, a 27-gon. So that's that. You might want to put that in your notebook in case you forget it somewhere. But here we have example 2. And in example 2, it says the poles for a tent form the vertices of a regular hexagon. When the poles are properly positioned, what is the measure of the angle formed at a corner of the tent? Now we don't need a diagram. I could totally draw one for you if you'd like. But the important thing here, and I went ahead and to show you how important it was, I went ahead and highlighted the word regular. You have to remember that in chapter 1, a long, long time ago, we learned what regular meant. A regular polygon is a polygon whose sides and angles are all the same. So unlike the previous example where you had some angles that were different, I mean, one was 135, one was 45, two of them were 90. Not all of the angles were the same, not all the sides are the same length. That is an example of not being a regular polygon. But when they tell you that you have a regular polygon, you are supposed to assume, they're going to assume that you know what that means. So this is very important, because if all of the angles have to be the same, and we already have a formula for how many degrees are in the polygon, all we have to do is divide by how many angles there are. And there are the same amount of angles in a polygon as there are sides. So a triangle has 3 sides, but it also has 3 angles. A pentagon has 5 sides, but it also has 5 angles. And here we're talking about a hexagon. And so in a hexagon, the number of sides is 6. All right, so it says, what is the measure of the angle that is formed at the corner of the tent? So basically you have this tent, and it's a hexagon. So you've got these, let's see if I can do this right here. It's going to look something like this. Okay, and all the sides are going to be the same. They're all going to be the same. And all the angles are going to be the same. And what they want to know is, once you position everything properly, what is the measure of the angle that's formed at a corner? So this would be the corner. So they want to know what this angle is. All of the angles will be the same. So what we have to do is, first and foremost, figure out how many degrees are in the figure altogether. And that's going to be 6 minus 2 times 180, which is 4 times 180. Which gives you 720. So this figure, all of these angles together are going to be 720 degrees. But furthermore, because they're all the same, we can go ahead and divide by 6, because that's how many angles there are, and they all have to have the same measure. So 720 divided by 6 gives us 120. So the answer to this question is that it will be 120 degrees. So now you can try this example, and again, remember that it says regular in both scenarios. And then we'll move on to example 3. Example 3 says, the measure of an interior angle of a regular polygon is 135 degrees. Find the number of sides in the polygon. So now we have to go backwards, okay? We know that we have this little guy. When something is regular, we took n minus 2 times 180, which basically represented the interior angles sum. Because it was regular, so I just kind of want to show you what's happening. Because it was regular, we also divided that by the number of sides. Because the number of sides is the same as the number of angles. And each angle had to have the same measure. So at the end of the day, each angle measure was equal. This was the individual angle measure. It's a formula, so if you will. The individual angle measure for a regular polygon is to take the sum, which is n minus 2 times 180, and divide it by n, because that's the number of angles. So all we're really doing here is kind of going backwards. We already know what the individual angle measure is. They're telling us that one of these angles, the measure of an interior, one interior angle is 135. So we're going to make this equal 135. Furthermore, we know that it's, and we don't know what n is. We don't know the number of sides. So we have to solve for n. So we know that 135 equals n minus 2 times 180. So we're going to distribute the 180 to the n. So that's going to be 180n. And then 180 times negative 2. So that's minus 360. So we're just kind of working backwards from our formula. Divided by n. Now to solve, we're going to times both sides by n. So that the n's over here are going to cancel. And I get 135n equals 180n minus 360. Then we got to put the the ends on the same side. So 135 minus 180 is negative 45n, equal to negative 360. Our last step is to divide by negative 45. And we get 8. So that means that the number of sides is 8, and so this was an octagon. So that's how you work backwards. When they give you the angle measure and they want to know the number of sides, you have to work backwards. So we want you to try to do it yourself, number 3, and then we will go on to the exterior angle sum. So I've drawn a figure for you here so that you can understand what the exterior angle is talking about. I want to remind you again what an exterior angle is. An exterior angle is an angle that is formed by the extension of one of the sides and a side. So you can't put 2 extensions and call that an exterior angle. That's not an exterior angle. It has to be the extension of one of the sides, which is what all these arrows indicate, that you're extending the side, and then the other side of the angle is a side of the polygon. So this happens to be a hexagon, and so it has 6 interior angles, and therefore has 6, actually technically has 12 exterior angles, because each vertex has 2. I could draw this out, and even though I said that this is not an exterior angle, this would be, this angle right here. So at each vertex there are technically 2 exterior angles, but according to the theorem you only want to use one at each vertex to apply the theorem. And so here's what the theorem states. It says the sum of the exterior angle measures of a convex polygon, one angle at each vertex. So you don't want to add 2 of them at each vertex, but if you have one exterior angle at each vertex and you add them all up, then their sum will always be 360. So in layman's terms over here, we know that I've drawn here one exterior angle at each vertex. So the measurement of angle 1 plus the measurement of angle 2 plus the measurement of angle 3 plus the measurement of angle 4 plus the measurement of angle 5 plus the measurement of angle 6 should all equal 360. Doesn't matter how many sides you have, the sum of the exterior angle, as long as there's only one at each vertex, will always equal 360. So now we can use that theorem here in example 4. It says find the value of x in the diagram. So what we know is that we have a quadrilateral here. The pentagon. 1, 2, 3, 4, 5. There are 5 exterior angles here. So we know that the sum of all of the exterior angles, as long as there's only one at each vertex, if we add them all up, they should add up to 360. So it's going to be very simple. We're going to start here with 2x minus 5. Add that to 3x plus 10. Add that to 6x minus 5. To 2x. And to 5x. And it should all equal 360. So now I want to color like terms. So we've got 2x and 3x is 5x, and 5x and 6x is 11x, and 11x and 2x is 13x, and 13x plus 5x is 18x. Then you have negative 5 and 10, which is 5. Then you have 5 minus 5, which is 0. So that's it. 18x equals 360. Divide both sides by 18. And 360 divided by 18 is 20. And that's they wanted us to find the value of x. Now I forgot to write on the board here, but there is a part B, and it says find the measure of each exterior angle of a regular nonagon. So in part B, I'm going to make some space down here for part B. They want us to find the measure of the exterior angle of a regular nonagon. A nonagon is a 9-sided figure, okay? So again, you have to remember that if all of the interior angles, so this is not a good example, but let's just go here real quick. If all of the interior angles are the same in a regular polygon, then all of the exterior angles will also be the same. Because for example, if this interior angle was 80, then the exterior angle would have to be 100 because together they have to form a line and they have to add up to 180. So if this was 80, this would be 100, and then this interior angle would have to be the same as this one because it would be regular. So that would also be 80, and that would be 100, and 80 and 100, and 80 and 100, and 80 and 100, and 80 and 100. So they would, all the exterior angles would also be the same. So this is a really simple question to do. Because it's a 9gon, we have to know how many, we already have to know how many degrees are in the figure. We know that all the exterior angles have to add up to 360. And we know that there are going to be 9 exterior angles. So you just divide 360 by 9, which is going to be 40. So for part B, which I apologize I did not write down, it asked us to find the measure of each exterior angle of a regular nonagon. So that's how you do that. It would be 40. So now you can try this last example here. And once you have finished this example, you will have completed your notes for this lesson. And I will see you in class, and thank you for watching.